Good morning, everyone. How are you today? Good morning, Raphael. Looking good with the headset there. Looking good. All right, we got a few things to do today. We're going to get right to it and right to our homework. Okay. Good morning. It's a Monday. Here we are. Exam is this Thursday. We'll talk more about that in a few minutes. So let me stop sharing this and go to my document camera. Get my controls over here. There we go. One second. There we go. That's what I wanted to do. All right, everybody can see the homework sheet. Thumbs up. All righty, there we go. Okay. Just 1 second here. All right. So here we got a problem. It's going to be done in several parts to show the impact of sampling. The length of the long distance telephone calls have a mean of 12 and a standard deviation of 4. If a random sample of 100 calls is selected, what's the probability, 1 or I? What's the probability that the sample mean X bars between 11 and 13 minutes? Okay, well, the first thing we need to know is we know we have a sample, so we have an N, so we have a sigma. So usually if an N and a sigma, it usually means you have the standard error, which means sigma over radical N. So in this case, sigma is going to be 4 over square root of 100, be 4 over 10, or 0.4. Okay, so it's going to be 0.4 for all these problems. All right, so what we want to do is we draw a graph here, right? The mean is 12. We want to know the probability is between 13 and 11. Now I know by symmetry, if we get this area here, we can double it. So let's do the Excel command first. The Excel command is going to be from the 0 point up to 13 minus the 0 point to 11 to give this net right here that corresponds to this area right up here. So the Excel command is going to be normdist 13 12.41 minus normdist 11 12.41. Remember, there's two curves, right? So if we do, this is the X curve, this is the Z way. So doing the Z way is going to be Z equals X minus mu sigma over radical N, right? So notice this is a standard error because we're talking about the mean of a sample, right? So again, we can just do this half here and multiply it by 2. So we can do 13 minus 12 all over 0.4, right? Because 0.4 is this number right here. We just calculated this already. That is that, which translates to that, right? So that's 1 over 0.4, which corresponds to 2.5, okay? my handy dandy Z chart, right? 2.5, right? 2.5 is this value right here, 0.4938. Right? 0.4938. Well, 4938 is this area, which is this area here, right? So we can take that, multiply it by 2, we're going to get an answer of 0.9876, okay? So this here, underlining in green, is the Excel answer. This answer here is the actual answer, right? So remember, we are doing many of these calculations as we did with the binom dist and the Poisson. We're showing you how to do them on the Excel way. If you have a calculator that actually does the calculation, that is irrelevant to me. That is not an answer. Some people on the quiz you took recently gave me answers for the Poisson. I did not want that. I wanted the Excel command. So if you did not give me the Excel command, you got no credit. Okay, so the Excel command is the answer if I ask for the Excel command. So that is the only, this has Excel command, this is the only acceptable answer. This has actual answer, this is the only acceptable answer, right? You may know the Excel command, good for you. You made the actual answer, good for you, but you got to answer the questions being asked. Any questions?
Professor, so for this one, we were able to do just like multiply by 2 because it's equidistant from 11 to 12 and 12 to 13, right?
Correct.
Or,
correct.
Okay, so if it's like 10 to 12, then to 13, that's a different story, right?
Right.
That's,
so if indeed this was not symmetric, you'd have to do each side. So you would have to do this side and do this side, right? So if the answer was, so right, if it was 10 to 12, you would have to do from 12 to 13 like we did, and then do 10 to 12 and add them together. So the fact that we can do symmetry, that just happens to be a characteristic of this specific problem.
Got it. Thank you.
You're welcome. All right, the next question, same problem, right? Sigma of 4, standard deviation, sample of 100, mean of 12. So again, your standard error, SE, standard error, is sigma over radical n. It's still 0.4, what it was in the last problem. So now, what's the probability x bar exceeds 12 minutes? This is question II, as in yikes. Okay. Now, this is an easy question. This answer, right? Here's 12. It really wants this answer, right? The answer is 0.5. Right? We know due to symmetry, it's 0.5. This is an easy question. Do not write an Excel command for this. If someone asks you to do an Excel command, you say, come on, we don't have to do an Excel command. We know it's 50%. Excel command is for something you want to figure out. We know by the symmetry rule that it's 50%. Don't ask me to do that. You're wasting my time. Right? So again, this one here is a trick question. Okay. Again, you want to keep it. The reason this question is in here is to demonstrate the importance of symmetry. Right? That is so critical, and that's what people forget all the time. Make sure you understand symmetry, 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 symmetry. All right. The length of long distance telephone call to the mean of 12, 4 thing, standard error is still 0.4 in this problem. What's the probability the sample mean x bar exceeds 12.5 minutes? So here's our x line. Again, here's 12. Again, does not need to be to scale. So 12.5, whoops, 12.5 is here, right? And we want to know what? We want to know all of this area. Okay? So the Excel command is 1 minus norm dist, 12.5, 12.4, 1. Remember, right? You may need to calculate it. In a problem like this, you're not going to be told, rarely will you be told what the standard error is. You're almost always going to need to figure it out. Again, if they're talking about the mean of a sample, third time, mean of a sample, you're always going to use the standard error. Okay? If they're talking about the mean of an average, it's a standard error. If we're talking about just the average of a single unit, that's just a standard deviation. I'll say it again. If you're talking about the mean of an average, meaning several points, use a standard error. If I wanted to know just the likelihood of one unit, it's just going to be a standard error. Standard deviation. If I want to know the average of one unit, it's just standard deviation. Okay, so the z-way is going to be, again, it's z equals x minus mu over sigma over radical n. So it's going to be 12.5 minus 12 all over 0.4. So 0.5 over 0.4 is 1.25. Okay, looking at my handy dandy z chart, right? I look for 1.2, and I go over 1.25, right? Which is 0.3944. My finger's right on it, 3944. Remember, 3944 is distance from mean, right? Which means it is 3944 is this area.
Professor, could you adjust the camera, please?
Yep, thank you. Right? 3944, distance from the mean, is this area here in red. That's not what we want. So 0.5 minus 0.3944, right? is 0.1056. That is your answer. And this is your Excel command. Questions? IV, as in one of those schools across the river at BU, right? So again, mean is still 12, standard deviation is 4, still a random sample of 100. Your standard error is now still 0.4. What's the probability the sample mean X bar is under 11.2 minutes? You can draw the graph. 11.2 is over here, right? We want to know this area right here is your X line, right? So again, the question mark is here, so you know you're doing a norm dist command. So this is norm dist, 11.2, 12.4, 1. The z-way, z equals x minus mu, sigma over radical n, 11.2 minus 12 all over 0.4. 11.2 minus 12 is negative 0.8 over 0.4, negative 2. There's a z curve, right? This is 0. Negative 2 just means to the left, so negative 2. Okay, again, this area and this area are the same. Okay, again, looking at my z chart, 2 is 0.4772. .4772. 0.4772 is distance from the mean. It's this area. Is that what we want? No. So we've got to do 0.5 minus 0.4772, which equals 0.0228. That is your answer. And this is your Excel answer. Questions? Again, V, as in the letter after W. That's our mean, 400. So again, the standard error is still 0.4. There's a 90% chance that the sample mean X bar will be above how many minutes? Okay, so 90% of the 97% chance will be above how 90 above one what value? So clearly what you have here, here's your mean of 12. We want to know what is the value where all of this equals 90%. So the question mark is on the X line. So I told you, if the question mark's on the N line, on the X line, that means what? It's a norm INV command. Norm INV, okay? The distance from the 0 point is 0.10. Whoops. Norm INV, 0.10. The mean of 12. Standard deviation, or in this case, the standard error, is 0.4. If we look it up on the Z table, again, the Z table starts in the mean. If this whole thing's 90%, then you know by default, this area here has got to be 50%. This here has got to be 40%, because the 40 and the 50 equals the 90. So again, what you're going to do here is you're going to look up 0.4000. So in your Z chart, we've done this already. Make it a little bit bigger, right? You look around, look around, look around, up, okay. You're getting close over here. 393939, oh, 3997 and 4015. Remember the first rule. The first rule is take the ones that's closer. So the closer value is this one, 3997, which equates to 1.2 and then 8. Okay, so 1.28 equals X minus the mu of 12 all over 0.4, right? So 0.4 times 128 is 0.0512 equals X minus 12. Add 12 to the side, okay? It's 0.5. So then it ends up being 12.512 equals X. I'm counting. 11, 12, 13, 14.
Why is it smaller than 12?
Why is what?
The value X.
Yeah, what about it?
It's to the left of the chart. Shouldn't it be bigger?
Bigger? Or I mean smaller?
Smaller, yeah.
Thank you. Everybody else isn't paying attention. I did this on purpose. This is the wrong value. This value here is over here. 12.5 is to the right. How can it be 12.5? It's going to be less. I made a mistake. What's the mistake I made? Negative, right? It's to the left of the mean, right? So you take 12, you minus 0.5, right? So the answer is going to be 11.48 or something like that, right? So 11.48. This here, this negative sign is one of the most common mistakes that students make. Again, it's the reason why you should draw the graph, right? Good job, Ryan. Took you a little longer than it should have, buddy, right? You get a gold star for today, but everybody else wasn't paying attention, right? Remember, I'm here as this class. This is not an online. This is not something where you're watching a recording and just kind of going your merry way. This is supposed to be interactive. So I'm going to test you, and I'm going to make mistakes on purpose to see if you catch me. Right? So clearly, there's supposed to be a negative. All right? Now, while we're on this problem, okay, I'm going to make another comment. Right? Ready? Never never 1 minus norm INV. Never. Never. Don't dare think about writing that. Right? Norm INV, that is not a command. Right? Norm dist or 1 minus norm dist. Binom dist, 1 minus binom dist. Poisson, 1 minus Poisson. Never 1 minus norm INV. Okay? Never 1 minus norm INV. Okay. This problem we just did, I'll exemplify that. All right? Right? Okay? So let's say you screwed this up. So let's say you wrote norm INV. You wrote 1 minus norm INV. And you wrote, you said 90%, so you wrote 1 minus norm INV of 0.9, comma 12, comma 0.4. Well, norm INV of 0.9 would give you a value up here, right? Because again, norm INV would give you the break from 90% or above, right? So let's say that value, I'm just going to guess. Let's just say that value is 14. 1 minus that value is 1 minus 13, 1 minus 14, which equals what? Negative 13. If this is 12, zero's over here, negative 13 is all the way over here. You're not even in the same country, right? Not even the same country. So 1 minus norm INV would give you a value over here. It's not even on the same chart. Never 1 minus norm INV. if you ever see that as an option on a multiple choice question, never choose that one.
Professor, I have a question.
I have an answer.
So for that problem, why did we try to look for 0.4 in the z table? Because I tried to look for 0.1.
But it's always distance from the mean.
Oh, shit. Okay. Yeah, that's right. That's right.
But Ryan, you made a mistake. You're never going to make that mistake again now, because you're going to understand. So again, there's always distance from the mean. Yes.
Yeah.
Remember, again, that's one of the biggest things. That's another common mistake that people just don't seem to stick in their heads, right?
Mm-hmm.
Excel from the 0 point or the left. Z-way, meaning the Z table, starts in the middle or the mean. That's a great question. So don't feel bad that you know a lot of people get that wrong, right? So again, Excel starts here. Z table. Start. Right? This is positive. These are negatives. Again, very common mistake. Any other questions? Questions are good. Okay. The length of long distance telephone calls has a mean of 12, standard deviation of 400, right? Again, standard error is still the same, 0.4. The lowest, 20%. Right? This is 20%. Okay. Will be below what minutes? Now this is easy because Excel, that's the starting point there. So this is just norm INV. 0.2, 12, 0.4. Okay. All right. Now this one we do a little bit differently, because if this is 20, what is this area here? 0.3000, 0.30%. So you need to look up that value. Look up on Z. Okay. So this one here, right? Look for 0.3000. Okay, 299, up here is 2995 and 3023. Right? 2995 and 3023, which is closer. This one. So that's 0.84. 0.84. So therefore, on my Z table, and again, this is my Z, right? This is 0. This is 0.84. It's to the left, so it's negative 0.84. I'm not gonna make the same. I'm not gonna make the same mistake. I'm not gonna make the same mistake I made in the last problem. Right? So negative 0.84 equals x minus 12 all over 0.4. When I do this out, excuse me, I believe it's equals 11.66, which is this value, which is that value right there, which is that value right there, rather. 11.66. So again, this is the Excel command. This is the actual answer. Okay. Same thing, 12, 4, 0, okay? To answer the above questions, do you need to assume that the probability distribution of individual long distance phone calls is normally distributed? That is a yes or no answer. Also known as a true-false answer. Someone unmute yourself and tell me, do you need to assume it's it's normally distributed or not?
Yes.
Okay, Ryan says yes. Does anybody else say no? Okay. I want everybody to think about this. Right now, Ryan has said yes. The answer to this question will determine whether or not you have a quiz at the end of class today or not. Right now, Ryan is your spokesman. So if you say yes, I'm going to ask Ryan or somebody else to tell me yes and then why. If someone else wants to say no, you say no and tell me why. A quiz is riding on this question.
Is it because of the central limit theory?
Well, first of all, tell me, is it yes or no?
It is a yes.
It is yes, okay. And the central limit theorem, what do you mean?
Because like we're having a sample size of more than 15.
Okay. Going once, going twice. Looks like we're having a quiz today. The answer is no. This is a very common trick question. And I gave you the hint. The hint was the word assume. Assume. Okay? Do not assume you know it is normally distributed because of the CLT. So Ryan, you had it correct. It is the CLT, right? But again, you do not, assuming means you make the assertion. No assertion, you know it is, right? It says, if there's more than 15, you are 100% positive it'll follow a normal curve. 100% positive. Ryan did a great job. No quiz today. You guys all said no quiz today. Right? I was trying to get you guys to think. I don't want anybody stressing about a quiz. No quiz. All right. Any questions on this problem? This is a problem that deals with the central limit theorem. Okay. So now, what it says here, it says repeat the odd number subparts, but the sample size is now 4 instead of 100. So let me find my pieces of paper here. So I'm going to be able to redo these pretty quickly. Okay. I'll do this in blue. Okay. So now what you have is your standard error is sigma over radical n, but now it is 4 over square root of 4, which is 4 over 2, which is now 2. Okay. So therefore, the Excel command is easy because basically, actually, I'm going to do this in red. Sorry, it'd be easier to see. Right. So now what happens? This just becomes 2. This becomes 2. Right. Down here, it's 13 minus 12 over not 0.4, but over 2. So this becomes 1/2. So 0.5 on your Z chart, 0.5 on your Z chart is right here, is 0.1915. So 0.1915 times 2 is 0.3830. So this is your answer. This is your new answer. This is your original answer. Okay. We're spending a lot of time on this problem, right? We've done all these subparts. Let's see why. Okay. Does this make sense? Here's my number line. Here's 12. Here's 13. Here is 11. Here's 14. Here's 10. Okay. With the first problem, 98% of the values were between 13 and 11. So that meant roughly the graph looked more like this, where all of this, again, a little lopsided, is roughly 98.76%. The other one is 0.3830. So that means roughly that graph looks more like this, where all of this area is roughly 3830. This is the learning from this problem, right? So this is the answer to part A, or part 1, and this is the answer to part B, right? So what happened? The standard deviation the standard error went from 0.4 to 4, to 2. Remember, the smaller the standard error, the smaller the standard deviation of the standard error, the taller and thinner the graph. Now that it's 2, clearly it's squatter and wider. Right? This is the lesson from these problems, is to understand how it affects the curve. Make sense? Okay, let's go to III. Yikes. Okay, so again, the standard error in this problem is now changed, right? Because now it's 4, so this becomes 2. The Excel command is easy. This just changes to 2. Down here, what this becomes, rather than 0.4, ends up being 2. So 0.5 divided by 2 is 0.25. 0.25 is this value here, 0.0987. Right? 0.0987. Remember, that is this area here. So 0.5 minus that is 0.4013. Right? So here's the first problem. Here's the second problem. Let's take a look at that and so we make sure I understand what that looks like. Here's 12. Here's 13. Here's 11. Here's 14. Here's 10, right? This question is asking exceeds 12.5. So here's this point, okay? So with the first one, right, the mean looks like this. Right? This is 0.1056. With the second one, right, 0.4013, right? So again, the standard error for the blue one is 0.4. For the red one is 2, right? This is larger, so it is squatter and wider. 0.4 is narrower and taller. Part 5, or part B. Okay. So again, same thing, 90%. Okay. So in this one, again, the standard error changes from 0.4 to 2. The norm INV command is easy. This becomes 2. So down here, it becomes 2 rather than 0.4, right? So now it's 2.1. It's 2.1.28, which is 2.56. It's negative equals x minus 12. So you subtract this. X is going to be 9.44. So 9.44 versus 11.48. Again, let's see what that looks like. Okay. Again, here's my 12. Here's my 11. Here's my 13. Here's my 14. Here's my 10. Here's my 9. Here's my 15, right? Here's my mean right here, right? Right? So the first one said, right? It was 11.48 was 90%. Okay. And the second one, 9.44, right? So this one here shows that basically looks like this, right? 11.48 here, where all of this is 90%. For the second one, 9.44 is here. That graph looks more like this, where all of this is 10%, but more importantly, all of this is the 90%. So again, all these three graphs have all been the same, right? The one with the standard error was 0.4 are all the tall blue ones. The ones where the standard error became 2 were all the short ones, right? Again, understanding how the graph changes is really the point behind this problem. The last problem is back to number 7 again. Ryan, we're gonna give you a chance to make sure we have no quiz today, just to verify. Now, with the standard error was 0.4 n of 100. Now my n is only 4 with a standard error of 2. So now, Ryan, do we need to assume that the probability of distribution of individual long distance phone calls is normally distributed? The answer is clearly, you're muted.
Now we can assume. Now we have to assume it's gonna be yes.
Correct. Right. Because since your n is less than 15, you cannot invoke the CLT. right? Okay. The last point about this problem, question. Answer. Right? Is your distribution normally distributed? Yes, because n is greater than 15. That is not the answer. The answer is yes, since n is greater than 15, you can invoke the CLT. This here is too cryptic. This is like saying, Mom, can I go out tonight? And she says, no. Why? And the answer is because. That's not a reason, right? Mom, can I go out tonight? No. Why? Because we have to get up early tomorrow to catch the plane at 4 in the morning. Oh, right? So this is a cryptic answer, doesn't make sense. This, just because n is greater than 15 doesn't mean it's normally distributed. Again, you have to invoke the CLT, meaning use this, because due to the CLT, it's normally distributed. Remember my role. My role is to teach you statistics. I am not here just to teach you a bunch of problems so you can take a test. All right. These last couple of problems are pretty easy, right? Suppose the distribution of weights of a large batch of items is normally distributed with a mean of standard deviation of sigma. If we take a sample of 100, right? So basically what we're going to do is we're going to take, you have the standard error of 100. The answer to the question, what's the probability that x bar is greater than 1.5 mu, right? Depends on the value of mu, but not the value of sigma. Depends on the value of sigma, but not the value of mu. Depends on the value of both mu and sigma. Does not depend on the value of sigma, nor the value of sigma. Depends on how many home runs David Poppy Ortiz. Again, he's an old Red Sox player that retired a few years ago. So clearly this is not your answer. Well, the answer is this one, right? Because remember, I told you this. When you say something follows a normal, you must know something about the mean and the standard deviation. Otherwise, you can't do any predictions about it. So the answer is going to be C. '61, which of the following choice is true regarding the probability of x bar for the sufficiently large sample size? So it's going to be very large, okay? Has the same shape of the population distribution with a smaller mean and a smaller standard deviation. Well, clearly, that's not true, right? Because you could have something like this, and you could get a mean that's on this side. So the mean could actually be greater. So that's not true. It has a normal distribution with the same mean and population distribution, but a smaller standard deviation. That is true. This is the true statement, right? Because your n is going to be smaller than the real n. This is the population number. This is the population. This is the sample. The sample is always a smaller proportion of the population. The same shape mean standard deviation of the population. That's not true. It's the same shape mean population with a smaller standard deviation. That's not true. These are normal distributed with the same mean. That's not true. So the answer is going to be B. This problem and the one prior, don't worry about that. I'm never going to give you a question like that on the test. You know, from today you really want to know how to, you know, the effort and understanding mean of a sample, right? we're about to take a break. I'm going to make a point. Remember what I told you about the red pen. Some things I say in class, I'm just going to say, you've got to make sure to pay attention. Okay. Okay. You've got a problem here, and you're given a mean, you're given a standard deviation, and you're given a n. Oh, I'm not going to say that. Sorry. Right? If the question, if you have this as a given, right? Which is why one of the reasons I do this is I write down what is known, because you know your answer is usually given, you know, you're going to solve the answer given using the variables that you're given, right? So if I see this and I see this, I almost always know I'm going to use sigma over radical n, almost always, but I got to be careful. So if the question asks you something about mean of the sample, you are definitely going to use the standard error. On the other hand, if the question asks you something about only about one unit in the distribution, that is just sigma. Example. Sigma is 2, mean of 20, n of 64, right? Okay. So it says, question says, blah, 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 probability that mean of sample is greater than 25, right? So you're going to do 1 minus norm, again, just do the Excel way. 1 minus norm is 25, 20, and you're going to do 2 over square root of 64, comma 1. On the other hand, is the probability of getting 1, again, let's say these are, you know, boxes, right? These are boxes of something. Getting 1 box more than 25 pounds, let's say these are pounds, more than 25 pounds, that would just be 1 minus norm dist of 25, 20 to 1, right? Right? Mean of the sample, probability of getting 1. So in this instance here, you are not necessarily using everything you're given. That is rare, but it could happen. Do not be fooled. I come back to do you understand what it means? As everybody's seen when you've done some of the quizzes and done the exam, right? I don't always word things the same way. So you need to be discerning in how you read the questions, right? Read the questions carefully, right? So when it comes time to take the exam on Thursday, I would not read the question and start writing something down. Take time to read the question. Certainly, as I mentioned in last class, before, certainly with this exam you have on Thursday, I don't think it's not going to be any harder, I think, in difficulty as opposed to exam 1. Okay, but certainly you probably want to have some scrap pieces of paper with you so you can do some calculations, right? And clearly, I'm telling you, I'm suggesting, please, please, please have a scrap piece of paper, draw the graph. It will definitely help you make the problem. Okay, now, we're about to take a break, but I do want to make a comment. The comment I want to make is many of you did well on exam 1. Some of you got, there were some people who got hundreds. There were many of you get like 96s. You got like 1 problem wrong, which is very good. Very proud of you. Do not rest on your laurels, meaning don't go into this test thinking, oh yeah, I got it because I did so well on the first test. That is a mistake. I would say, again, I've done this for 20 years. And again, I want you to do well. I want to give you an A. You need to earn it. Okay? I would say in my past experience, and again, I've done this fall, spring, summer sessions 1 and 2 for years. And again, I think I counted it basically, I think last year, I think I've taught over 5,000 students in this course. Okay. Inevitably, if I have if in a class, if I get 8 people that get hundreds, if I get 8 people that get hundreds on exam 1, 8 people on exam 2, half of them get like a 70 on the second test. Because they said, oh, no, exam 1 was kind of easy. I thought it was easy. So the next one's gonna be easy. And they find, oh my gosh, it's not easy. Do not do that, right? So if you studied hard for exam 1, good for you. Study hard for this one, okay? Now, before we have break, for those of you that are feeling a little overwhelmed, maybe a little lost, please, please, please email me, right? I will gladly meet with you individually or of office hours sometime this afternoon or this evening. The same with tomorrow, right? So I will gladly set up a time with you. We can have an individual session, or if a bunch of people email me rather than individual sessions, again, I'd like to do everybody at once as opposed to spending all this time. But I definitely will meet with you, right? So again, if you want to meet later this afternoon, again, this East Coast time, you want to meet, after 4 o'clock or sometime even like before 9 o'clock tonight, no problem. Okay, again, I am telling you, please, 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 if you want to meet with me, send me an email, right? And I will set something up with you, okay? I'm more than happy to do that. Again, my role is to help you understand material. I am making myself available. Some of you are staying after class to talk with me. Some of you are not. That's fine. I mean, again, I don't know if you need help or not need help, but if you are feeling a little bit lost, or want to have some, some other stuff. Again, you can ask me any question you want, right? And again, I'm not judging anything. If you want to ask me something about basic probability, I'll gladly go through it. Okay, again, I want you to do well. I want to try to coach you and teach you. Okay, all right. We're gonna take I gotta have my coffee, so we're gonna take like a 15-minute break today. 15-minute break today, and we'll come back and continue. All right, see everybody in a few minutes. Be right with you, everybody. Sorry. Be like 2 minutes. There we go. Sorry, everybody. A little few technical difficulties here this morning. All right, so we're going to go into our discussion about today's topic. Actually, there's two topics today. We're talking about interval estimations and also talking about standard deviation being unknown. Okay, so we're going to talk about those two. So let me screen share with you and bring up that PowerPoint. All right, everybody can see the PowerPoint, thumbs up. Great, thank you, everyone. Okay. My coffee. All right, so what we're doing here now is, again, we've learned a lot about probability. And we've talked about the different ways in probability. We've talked about using sampling once you knew something about like Bayes' rule. We've talked about counting techniques, which how you use large numbers. And then, like I said, the analogy that I use for the baseball players or for a game, basic probability, are they going to win the game? And then, okay, if you know something about how the team's performing, oh, they do better when they're away versus home. Oh, it's an away game, they're going to win, or they're going to lose. Then we may know something about a payoff table, understanding, okay, gee, what happens if they, under what scenario will they do well or not do well, right? So you have these list of different things that may happen, okay? What the weather is, whether it's a away game, who's pitching, and all that sort of stuff for whether they're going to win or not. And then you can do decision trees. And then from there, we talk about kind of different distributions. So we understand, okay, somebody may be a binomial where you're counting x of n, somebody who's a Poisson, which is a rate, or somebody could be a normal curve. Well, the thing is, lots of times you may want to know something about a population, but you can't survey everything in the population, right? That's the whole point. You can't go out and, if you wanted to know what everybody thought, if you want to know what BU students thought about the dining hall, the Union, the George Sherman Union down there on Commonwealth Avenue, if you want to know what thought about that, yes, you would love to do a survey and survey everybody at BU. Not really practical, right? Again, a lot of people aren't going to respond. So what do you want to do is you do a sample. So by sampling, you can still get just as accurate information, right? And that's very useful, right? So, if you follow politics, certainly in this country, what's going on now, we have an election coming up basically in a few months from now. If you want to know whether a political party, what their feelings are, right? They have samples. So they do a poll, and the poll is they talk to 1,000 random people or a couple thousand random people and get their opinions on the president, on the challenger, on some kind of economic policy, about COVID, blah, blah, blah. And from those samplings, they can then make some assertions about the population. That deals with our first topic today, deals with interval estimation. So basically by doing a sample, can we then make a prediction about the population, and then how accurate would it be about the population, right? So that's kind of where we're talking about. Okay, so let me bring up my laser pointer here. Okay. So let me just change things around just a little bit here. Change my screen a little bit. This is what I want. Great. Okay. All right. So what you may want to know is we may want to know what's called a point estimate. So a point estimate is if we want to know what the average, everybody that took a test, right? So you've got people that took the SAT. Maybe you took the SAT or the SAT or TOEFL or something like that to get into BU, right? So if you wanted to know what the an average was of everybody that took it, and you don't know what the average of everybody that took it is, your best guess would be what would be the sample average, right? So if you sampled 100 people and you found the average to be 75, that's probably a pretty good guess as far as what the true average is. Again, that's always your best guess. Okay. All right. So what we can know is we know basically that the best guess that you get, again, the 75 has some error. It's about 75, give or take something, right? Now, again, you talk about that as well. When you talk, in your everyday life, you may talk about, hey, how likely is it that you're going to go away this summer? Well, I think it's an 80% chance it may go away, give or take 10% or so, plus or minus 10. Okay. How likely you're coming back to campus in the fall, right? You're going to be in the fall. Well, maybe 75%, give or take 5% or so. So maybe between 80 and 70% chance, right? So again, you have that range that you have there. So what that is known as is, you can see it's X bar, that's the 70% or the 80% I just said in my example, minus some range, 5%, 10%, and then the same value plus 5 or 10%, right? Again, so basically it's an interval. It's an interval. Now, an interval has a couple of characteristics. Again, I'm pausing to make sure you listen to me. A couple of characteristics. One characteristic is that it is always 2 points, right? Has a lower point, upper point, and they are symmetric about the mean, right? So if you get a sample and you think it's 75, it's 75 plus or minus 10%, right? The lower end is going to be 65%. The upper range is going to be 85%, right? So, and that 5%, that's known as this thing as known as E. Now, again, this is little e. Capital E means expected. Little e is known as the margin of error. Margin of error. Margin of error. Now, again, I'm going to stop sharing here, and I'm going to show my document camera again real fast. Okay. So again, if you sample 100 people, find X bar equals 75, right? So the range is 75 plus E, 75 minus E, right? Symmetry. So this area here has got to equal that area there. They've got to be symmetrical, okay? And this here, E, is known as the margin of error, right? Certainly, if you follow any kind of politics, they always talk about that. If they talk about a candidate, he's got a 52% approval rating, and they say the margin of error is 3%. So if 3%, that means really this person's approval rating could be 49 and it could be 55, right? So it's somewhere within that range, right? So depending what E is will depend on how wide that range is. If the margin of error is 10%, in this case, it would then be 42 to 62%. So it'd be much wider, right? So that's why it's partnered with the margin of error. Now, E, I'm going to give you the formula now. We're going to talk about it in a couple of pages. E is Z 1 minus alpha sigma over radical N. Right? I'll explain more about this in a minute. But again, so the advantage is you know that if you E, you can substitute this formula for 75 plus E, you can calculate what that value is going to be. Again, we'll get to this in just a minute. All right, so let me go back to my PowerPoint. All right, so interval, okay? So it's such that, so basically it's X bar minus E, X bar plus E, such that the lower limit, X bar minus E, is less than the mu, less than the mean, which is less than the upper limit. Again, this whole thing just talks about the symmetry I just did on my document camera. And that is equal to what's called 1 minus alpha. Alpha, this is the Greek letter A, 1 minus alpha, okay? Let me go back to my document camera real fast and talk about that for a second. One minus alpha is your confidence level, right? So if I write 1 minus alpha is 95, translation 95% confident. If I do 1 minus alpha is 90, that means 90% confident, right? So this one here, 95%, I would say, hey, here are my values. This value is 12, this value is 17, right? We're 95% confident that X is between 12 to 17. This one here, right? Again, we don't know what this is. Here, 90% confident may be, again, this may be 30 to 35. 90% confident that the mean is between 30 to 35. Again, this is just how you translate it. So this means this here is 95%. This here is 90%. That's what it means. So, right. So, and again, Ryan, when he did one of the first problems you did was you did 95%, we did the middle 95% rather than doing from the right, like the problem we did yesterday. Now we are talking about the middle 95% or the middle 90% or the middle 99%, right? We're always talking about that. So a confidence interval is always symmetric about a mean. So again, there's white space over here, white space over here, white space over here, white space over here. Okay, I'm going to share with you again. So again, if you have any questions, unmute yourself and ask questions. Okay. All right. So again, if X bar is 10, perhaps the interval could be between 8 and 12. Now remember, I told you it's symmetric. So if the mean is 12, if it's 10, 2 to the right is 12, 2 to the left is 8. If it's between 7 and 13, that's 3 to the right and 3 to the left. Again, symmetry. It's going to be always in the middle. Okay? So again, and it could be the confidence interval could be 95 and it could be 99. Okay? All right. Now, this is what I said. 1 minus alpha, I just showed this on my document camera, is the confidence level. Is by tradition, usually in this class, it's either going to be 90, 95, or 99. Again, certainly in this country and in most of mathematics, that's the way you talk, right? You know, hey, Joe, you coming to my party? Yeah, I think so. Well, I need to know if you're coming or not. You know, give me a probability you're going to show up. Well, I'd say like 83%. 83%? No one talks that way, right? Again, yeah, 90% sure or whatever. Again, you know, people don't talk 83%, right? So by convention, most times we talk about confidence levels, or they're usually 90, 95, and 99. Occasionally 80%, maybe 85 from time to time, but again, those are rare. Generally speaking, it's usually 90, 95, or 99. In this class, they'll almost always be those three values, okay? And again, by tradition, it's 95%. This is a potential trick question. Now, I'm not going to write this anywhere. I'm just going to tell you. Trick question. If I say, what is the confidence level for blank, 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 and I do not say the confidence level, by default, it is 95%. So if the actual specific number is not given to you, it is omitted, it is always assumed to be 95%. And that's not my rule, that's in all the statistics, right? So again, if the actual level is not given to you, it's always assumed to be 95. Okay, so X bar minus E to X bar plus E. X bar is the sample. Again, this is 75 minus 10, 75 plus 10. That's called the confidence interval. Again, I told you, confidence intervals are symmetric, has a mean, and the same distance to the right, same distance to the left. Okay? The one to the left is the lower confidence limit. The one to the right is the upper confidence level limit. Very simple. And E is known as the half width. Again, it's half the confidence interval because, again, it's by symmetry, also known as the margin of error. I just said it. Margin, also known as the margin of error. Okay. So clearly, the larger the value of the confidence level, the larger the value of E. Clearly, right? So again, if you have a value, you know, so let's say I have a box. I want to get my video back on here. Let's say I have, oops, sorry, wrong way. Sorry about that, everybody. Good morning. Everybody give me a nice big wave. Big wave today. Everybody awake? Thank you. Right. Good morning. Nice to see you. Thank you all for coming here. Again, we don't have a lot of people here today. There are a lot of people that are having issues right now. Again, some people in this class are actually traveling
back home and going to be under quarantine situations, and we have a few people that are ill. So for those of you that are watching these on recordings, send me an email. I hope you're all doing well, everybody's safe and getting better and stuff. So again, we miss you. Again, I get it. It's a tough semester this way, having to do this Zoom stuff. Anyway, so my point is, what if I have a box, and in this box I've got 500 chips, you know, poker chips, and they're all numbered 1 to 500 individually, uniquely, right? Again, what is the chance of reaching in this box and getting a chip 1 to 500 that's marked between 50 and 450? That's a rather large range. Well, that's going to be what, like 99%? Yeah, clearly it's a large range. On the other hand, what's the chance of reaching in that box? What if I want to get a chip that is between, let's say it's numbered between 70 and 90 out of 500? That is going to be what, a very small range. That probability is going to be very small. Again, the range is going to be small, the probability is small. If the range is big, the probability is big. Right? That's the point of this PowerPoint slide, right? Small probability, small range, larger probability, larger range. Which one is more precise? Well, the smaller one's more precise. That's more accurate. The larger one is a lot of variability, right? A lot of, yeah, it's 99% sure it's going to be that number. That's a wide range. Okay. All right. So our task is to determine the relationship between, we're trying to find out the relationship between 1 minus alpha, which is the confidence level, and E, which is known as the margin of error. Okay. So here is our normal distribution. Now notice a couple of things. Notice that what we have in the tails is actually what is shaded, right? Normally it was the other way. It was the middle part. What's it shaded, right? 1 minus alpha, that is your confidence level. 1 minus alpha is your confidence level. So therefore, if our confidence level is 95, that means this area that is unshaded is 95. That means the area that's going to be shaded has to add up to, both shaded areas got to add up to what? To 5%. Due to symmetry, what's in one tail has got to be, in this case, 0.05 divided by 2, or 0.025, right? So think about it. If 1 minus alpha is 95, 1 minus alpha is 95, then alpha must be what? 0.05. Right? Because 1 minus 0.05 is 95. Okay? If 1 minus alpha is 90, 1 minus alpha is 90, then alpha must be what? 0.1. Okay. So we can find out what these values are. So a 95% confidence is a norms INV. And again, these are of 1.96 and 2.576 or 2.58. I'll show these another way on the Z table in a second. Okay. Now, this graph here and the next subsequent PowerPoints, to me, they sound a little confusing. So I'm not going to spend a lot of time on this. I mean, pay more attention to what I'm saying as opposed to what I'm showing on the graphs. But essentially what we want to do is we want to know, right? We want to know what this area is here that is shaded, okay? Now, from before, right, it was always Z X minus mu over sigma, okay? Which is what we wanted to know. Okay, but now we have our sample. So again, it's X bar minus mu sigma over radical N. This, again, the denominator here is what? Is the standard error, what we just spent homework doing today, right? So again, so the interval is this lower limit minus this X bar minus mu less than the upper limit, right? So again, this is minus Z1 minus alpha. This is plus Z1 minus alpha, which is going to give you this formula. This is the exact formula I wrote in my document camera. E equals Z1 minus alpha sigma over radical N. And this is, again, this is a key equation. You definitely want to know this equation and write this down because you're going to be able to manipulate this to do a lot of fun things. All right, so let me go forward a little bit. All right, So we assume that sigma is known. Again, sigma is known. We're going to relax that in a minute. So E equals Z1 minus alpha. And what Z1 minus alpha means is the Z for that confidence level. Is that Z for that confidence level, which, and then times sigma over radical n. So really in this equation, 1 minus alpha is our confidence level. E is what's known as the precision, or also known as the margin of error. Our sample size really is determined how big it is, right? Our sample size, how many you need to do. Because many times what you may want to know is, okay, if I have a class of 50, and let's say I wanted to sample enough people to be 95% confident of getting an average of the true height. Again, we can't measure everybody in their classroom. We want to, okay, do we want to sample 4 people, 8 people, or 16 people to find the true average of heights? We can determine how many we should sample. Should we sample 4, should we sample 8, or sample 16? Okay. All right. So let me talk a little about this Z1 minus alpha for a second. Go back to my document camera. So if I want to be 99% confident, I write that as 1 minus alpha is 0.99. Translation is that is Z of 0.99. It's a Z of 99%. If I want to be 95% confident, that's a 1 minus alpha of 0.95. Translation is a Z of 0.95. Okay? So what that means is the following. With this one here, that means I have this graph here. It means I know that these values here, again, this is the Z curve. This is a Z curve. This is 0. All of this is 99%. So I want to know, what is this value here? What is that value there? This value here, this value here. Okay, so again, so if I know this 99%, 0.99, this area here, right? 0.99 divided by 2 is 0.4950. So again, if I go to my Z chart, okay, and I'm going to zoom in a little bit, right? I told you, look in the body of the table. Look in the body of the table for 0.4950. It's between these two values, 0.4949 and 0.4951. 4949 and 4951. So what I do is I look over here. That's 2.5. Back here, you take the larger one. This is all the way up here, 2.58. So therefore, this value I'm going to use for my Z is 2.58. This one down here, 95%, it's the middle 95%. So if all of this is 0.95, yep, let me back out a little bit. Thank you, Jialu. Right? So if this is 95%, right, that means this area here, and this area here has to be 0.05. Due to symmetry, it's 0.05 divided by 2. This is 0.05 divided by 2, right? So 95%, right, 0.95 divided by 2 is 0.4500. So 4500, again, on my document camera, look at my Z chart, right? 0.4500, that's what? Oh, that's that special one. That's that rule 3. Remember this? Right? This is the exception. For 45%, use 1.645. Right? So therefore, with this one here, right? This value here for Z of 95% is, oh, I'm sorry, I did that wrong. Sorry. 0.95 divided by 2, right? It's 0.4750. Sorry, 0.4750. My bad. 4750. 4750. Clearly, I have not had enough coffee yet today. 4750 is right here. And that equates to 1.9 and then 6. Right? Right? So that's wrong. So Z of 95% is 1.96. So that's one value. This is the other one. So that's what we mean. Okay. All right.
Professor, can I ask a question?
Surely.
Back what you were showing us writing on the paper.
Yep.
So what is the value 2.58? What does that mean?
2.558 is the Z value. C value for 99% confident.
Okay, what's the point of dividing 99 by 2?
Because remember the Z values start in the middle, right? So you got to find this area right here that's in red, and that area in red is 4950.
And then what did you use the 4950 for?
To look in the body of the table, I looked in the body of the table. I tried to find 4950,
Mhm.
right? 4950, which doesn't exist. You take the larger one, right? This is back to these rules right here, right?
And then
Remember we did these rules,
yeah.
right? So then you use this value. Whoops. They use that value of 2. You may use that 2.58 to solve a problem. Again, I haven't gotten that part yet. All I'm doing here is trying to show you when you see Z1 minus alpha, which is back in the PowerPoint, what that means.
So the 2.58, is that like the area of the red shaded area on the Z curve?
That's not. What that is, I'll show it to you. Very good question. This is 0, right? If all of this is 99% on the Z curve, this is a value of 2.58. That's 2.58 standard deviations to the right. This is negative 2.58. 2.58 standard deviations to the left, where all of this area that's shaded is 99%. For the second one I did, this is 0, where all of this area here is 95%. This is 1.96 and negative 1.96. Right? If I wanted to, I could telescope these values up to this one right here, right? So I can draw them on the same line, right? All of this in green is still 95%. And clearly, this is negative 1.96 here and 1.96 here. Excuse me, positive 1.96 here.
Okay, thank you.
You're welcome. All right. Right. So what I was just showing was Z1 minus alpha. Z1 minus alpha is the Z, that confidence level. That's what I mean. So 1 minus alpha is always your confidence level. So a Z for 99% would be 2.58. A Z for 95%, 1.96. Right? That's what I'm talking about. Okay. So, let me go back here 1 second. So once you know this formula, you can manipulate this formula to answer these questions: confidence level, precision, and a sample size. Okay, so for instance, okay, here's an example. We sample 120 people and measure how long each person takes to fill out a certain form. We find that X bar is 13.85 minutes, meaning we sampled all these people and we basically added up everybody, divided by 120, and found the average to be 13.85. Assume we know from past data that sigma is 1.56 minutes. Again, sigma is what? Is the average distance to the data points around the mean. So basically that's basically kind of like the average spread. Find a 99% confidence interval for the true average time it takes a person to fill out the form. So remember, 99%, I just did that, is this value 2.58. So I can basically do substitution. So E is equal to Z1 minus alpha sigma over radical N. So 2.58 times 1.56, which is your sigma up here, divided by the square root of 120, which is your N. You get a value of 3.68. So basically what that means is it is the true average time it takes for somebody to fill out this form is somewhere between 13.85 minutes, give or take 0.368 or 3.37 minutes, or between 13.48 minutes to 14.2818 minutes, right? So again, you want to know, okay, yeah, on average, yeah, it takes people roughly between 13 and a half and a little over 14 minutes to fill out this form. Okay, now what we can do is we can use this formula to find something else. Now we want to know the average number of pitches thrown in a Major League Baseball game, right? We want to know the estimate the average number of pitches. We wish to be 95% confident that we get an estimate within 10 pitches. Okay, this is a key word. This word within. I'll say it again. The word within. Third time, the word within. Fourth time, the word within. Fifth time, the word within. The number that follows within is always E. Is always E. The number that follows the word within is always the value of E. I mean little e. Okay, so and suppose we know from past data that sigma was 40. What sample size do I require? So now we're using this formula here. Using this formula here, we're not solving for E. E is known. We're solving for N. We want to know what the sample size is. Okay? So what we can do, right? Here's our original formula. If I multiply both sides by square root of N, I'll get N. Square root of N equals square root of N times E, Z1 minus alpha times sigma, right? And then I could square both sides to get N out from the radical. So that's why everything is squared. And then I divide by E to put E on its one side. So basically, using algebra, I can come up with this formula right here, the one I'm circling with the laser pointer. Now again, you don't need to solve it. You can just write this down. That's the sample size formula. So again, so Z squared for 1 minus alpha. So that's 1.96 squared because it's 95%. That's the value I just showed you on my document camera a second ago. 40 is your sigma. And your 10 is your E. So when you do this all out, it roughly ends up being 61 point something. This question right here, your answer for N, your answer for a sample size is always going to be an integer. Always going to be an integer. So in other words, you cannot say 61.4. Because how can you sample 0.4 of something? You can either sample it or not sample it. So 61.4 rounds up to 62. Now again, any fraction above a number, you round up, never round down. 61.4 does not round to 41, to 61, it rounds up to 62. If your answer is 61.001, yes, that's close enough to 61. Again, if you go out 2 decimal places and it's 2 zeros, 61.00, then that's 61. But anything above that should round up to 62. This is where I catch people on exams. Remember the red pen? Where I catch people on exams and I get people, some people that will get the answer wrong because I round down, round up. Okay. Here's our question. So this is the end of the first topic, and then I'm going to jump to the second topic for today. Okay. So everybody take a minute and do this problem. Bill, a manager of a paint supply store, wants to determine if the amount of paint contained in 1 gallon cans purchased from a nationally known manufacturer actually contains 1 gallon. It is known that the standard deviation for the amount of paint can equals 0.02. Random sample of 50 cans is selected, and the mean was found to be 0.995 gallons. Find a 99% confidence interval for the true average amount of paint contained in 1 gallon cans from a nationally known manufacturer. Right? So do this on a scrap piece of paper, give you a couple minutes, and then I'll do it. All right. So in the little thumbnail, I have my document camera, and I've written down what's important from this problem. All right. Right? So what we want to know is we want to find a 99% confidence interval. So that means we want to find what is this confidence interval around this value, right? Where all of this is 0.99. So we're going to find that value there and that value there. So we know it's going to be X bar plus or minus E. We know from substitution, X bar plus or minus Z1 minus alpha sigma over radical N.
X bar is 0.995. Z1 minus alpha is 99%. That's going to be plus or minus 2.58. And again, where did I get that number? I get half of this. So 0.99 divided by 2 is 0.4950. Look it up on my Z table, and that's 2.58. So 2.58 times your standard error. Sorry, everybody, you can see that. Standard error, 2.58, which is going to be sigma 0.02 divided by square root of 50. So it's 0.995 plus or minus. Anybody have this value? Anybody have what this is?
0.007.
0.007?
Yeah.
Okay. So what's 0.995 plus this and 0.995 minus this? Give me the two values.
The higher number is 1.002.
1.002. Yep. 0.99.
88.
Yeah, 988.
988. Yeah.
Right. So that's the confidence level. Right. So we're 99% confident that the true amount in 1 gallon is just slightly less to slightly over. So that's good. So basically, 1 gallon is in this range. So that makes us feel good about this. Right. That's good. Okay. So let me go to the next topic for today. Which is sigma unknown. Okay. I'm not gonna talk about this part here. We'll talk about the Excel tomorrow. Okay. But here, there are some changes. This is just like the Z formula. I'm about to show you my document camera. Okay. All right. So with sigma known, we use this formula. With sigma unknown, we use this formula. Now, notice how we have, this is sigma, this is S. This is something as known as the Z curve. This is known as the T curve, right? So we have a Z curve. Now we're changing things up. This is known as the T curve. Okay? I'll come back to that in a second. Okay. So in the formula, as I just showed you, you insert S for sigma, and it's a T curve rather than Z curve. I just talked about that when I showed you my document camera. So it's a different way to do this. Okay. All right. Don't worry about these T commands. These are Excel commands. We'll talk about these later. Oh, whoops. This is it. Okay. Yeah, let me, I gotta show you this off my thing here. Okay.
All right. So what I'm going to show here with you, I've got to bring this up. Give me a second. Can you all see the home page of the? Are you looking at my document camera? Looking at the home page of the website. What are you seeing?
Document camera.
Document camera. Okay, thank you. All right, that's what I want to know. There we go. Sorry. Okay. Okay. So on our website, under resources, down at the bottom is this thing called a T-table. There is not one in your book. So this is the one you must use. So the T-table PDF. Okay. All right. So I'm going to quickly print this out for me because I didn't have this with me. All right. So this is a little unique. Okay. So the T-table is very similar to the Z-table in terms of it always starts at the middle. Okay. So I'm going to show this in just a second. So I'm going to show my document camera once this thing prints out. And my printer is not working. Just give me 1 second here. All right, well, that's not working right now. So let me come back to this then. Oh, here it is. Okay. Everybody can see my document camera? Thumbs up. Thank you. Okay. All right. So what I've done is I've zoomed in on this a little bit. Okay. So the thing you've got to understand with looking at the T curve is you got to know this thing over here where my finger is. My finger is this column. It starts at 1, goes down, 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 right? It goes down this table. This is called the degree of freedom, right? It goes down to a bottom of 35. Then from 35, it jumps up, starts at 36 on this side and goes down this way, all the way down and ends at 70, right? So this piece of paper is only useful to a degree of freedom of 70. All right. So let me explain what this is. Okay. This is your Z curve. That's your Z curve. The T curve is just like it, only it is a little bit. It's a little bit squatter and a little bit wider, right? So what that means is, as we just showed in the previous slides we did a few minutes ago,
right? 99%. This was 95% was 1.96 and 1.96. On the T chart, 95%, right? Maybe negative 2.02, that's a negative, and positive 2.02, right? It's a little bit wider than the Z curve. And it's delineated by what's known as the degrees of freedom, DF, degrees of freedom, which is always X minus 1, right? So, I mean, N minus 1. So if your N is 30, your degrees of freedom are 29. If your N is 50, your degrees of freedom are 49. If your N is 25, your degrees of freedom are 24, right? It's always N minus 1, okay? So what happens is they determined a long time ago, and it actually was discovered. It was discovered at Guinness Brewery, right? So Guinness Brewery, right? So what happened was there was this guy there. His name was Gossett, and his job at Guinness was he was the guy to make sure the beer was. He was the inspector. He was to make sure the beer was good to drink. So again, what do they do? Think about a manufacturing process. Clearly, if they make 500 bottles of beer, they've got to make sure that the beer is, won't make you sick. So what they do? So they sample some bottles. So they run 500 bottles. They take a random, 20 bottles out, and they take those 20 bottles, they crack them open, and they check them. They make sure they smell okay. They may take a swig or something. They make sure the color's right. Again, all these things they do to make sure the beer is good. Now, obviously, they can't sample too much. Otherwise, after 10 o'clock in the morning, the guy's going to be falling down on his face. But so basically what he does is he does a metric, right? So he says, okay, and he comes with, okay, here, the bottles of beer, we know that the bottles of beer, we do all these things, right? And we know X bar, it's got to be within, it's got to be like 7.0, right? So it's going to be 7.0 over 10 for the beer to be good. And so when they do all these metrics, if they find out the beer was 6.8, that's not 7, there's a problem. And basically they would say, halt, stop the line, right? We can't have this beer going through here. And so what this guy did was he was sampling like 25 beers. And he would find occasionally that the value was 6.8 and said, oh my gosh, it's supposed to be 7. We've got a problem. We can't sell these beers. So rather than destroying the beers, what they said was, okay, the more you sample, again, we showed this, right? So with a small sample, the graph looks like this. If you increase N, the graph gets taller and thinner, it gets more accurate. And so they would rather than sampling 25, they'd sample another 25 and sample 50. When they sampled 50, amazingly, this number here many times went up to be like 7.1, and now it meant the beer was okay. So this guy Gossett said, I wonder why that is. And so he's the guy that actually came up with the statistical theory that became to be known as the T curve, right? Because essentially what it is the T curve is essentially, it's a family of curves. It's a family of curves that mirror the Z curve, but has a little more flexibility. It's a little bit wider. But the thing about the T curve is, and again, you can look at your T chart to verify this. Here's my normal curve, right? If my degrees of freedom are 10, the graph may look like this. If my degrees of freedom are 30, the graph may look like this.
right? See how it's looking more and more like a Z curve, right? If I then do my reason of 50 now, right? So basically, as this increases, more like a Z curve, right? More like a Z curve. So that's what we want to know. That's what you know for your precision, right? So it's a family of curves. And you use the T curve or T distribution when sigma is unknown, right? And then from that you substitute S. S is the sample standard deviation. Sigma is the population standard deviation, right? So let me go back to my PowerPoint and we'll do this problem together, and that will help bring it together and kind of connect the dots for you. Again, what you see now, you want to make sure to have this page earmarked. Again, I would argue you should print this out. You should have a T curve with you, and you should have your Z chart with you. It'd be a lot easier than try to do things electronically. Now, let me go back to my PowerPoint. There we go. All right. So here's what we have. Again, we're going to go back, right? So, right. So again, we're using the T curve when sigma is unknown. This is the critical point. When do you use this? When sigma is unknown, you're going to use the T, and you're going to substitute S for sigma and use the T curve rather than the Z curve. Again, we'll do this when we do homework tomorrow. Okay. Again, the T curve is always fatter and shorter than the Z curve. I just showed that to you, right? So say for a 95% confidence interval, you get a wider interval when sigma is unknown and S must be used. That makes sense, right? You want to be not as accurate. Okay. Don't worry about the TINV command. We'll talk about this later. Don't worry about the TDISC command. We'll talk about that later too. That's another class. Let's do this problem. We're going to do it together. Suppose we sample 9 people and ask whether they agree or disagree with how the owner of a local baseball team is running the team. There's a 7-point scale. One is strongly disagree, 7 strongly agree, what's called a Likert scale, and find the mean to be 44.1. That's an X bar. And they compute S. Again, that's not sigma. They compute S, the sample standard deviation to be 0.6. So therefore, we want to find a 90% confidence interval. Okay, so what we want to find is we don't have sigma, we have S, so we've got to use the Z curve. Okay, whoops, went away with this. Okay, so what we do then, oh shoot, I don't know why this is not here. It's frustrating. Let me use I'm gonna use my document camera. So based on this problem, our sample is not we sampled 9 people, right? We want to know how they're doing. The X bar is 4.41, right? We calculated our S, right? And our S is 0.6. And again, sigma is unknown.
Therefore, use the t-curve. Okay? So now we want to know a 90% confidence interval. 1 minus alpha is 90%. So it's still going to be x bar plus or minus e, right? Now e was z1 minus alpha sigma over radical n. Now, because we have s, we're going to change that. And now it's going to be e is going to equal t1 minus alpha s over radical n. So it's going to be x bar plus or minus t1 minus alpha s over radical n. Okay. So x bar is 4.41 plus or minus blank, right? We're going to solve this in a minute, but it's going to be times 6 over square root of 9. All right. So what we do then is, let me get my z curve. Where did I do my z curve? Here it is. Okay. So my z curve, right? What I'm going to do here is, we know from this problem n is 9, so our degrees of freedom are going to be 8. So then what we do, let me make this larger. Right? I can make it larger still. Right? So we know our degrees of freedom are 8, which is this line right here. This says our confidence level. We know from the problem that we want to be 90% confident. 90% confident is right here. So we go 90% confident, go down and find degrees of freedom of 8, and we see that value 1.860. 1.860. So then what we do is we can write 1.860. And then we can solve for this. Okay. What we did today, these are confidence interval problems. Right? It is okay to leave your answer in a formula, meaning an answer on an exam, it is okay to leave it like this. So again, I'll rewrite it up here. 4.41 plus or minus 1.860 times 0.6 square root of 9. This is an acceptable and actually a preferred answer. I'm assuming at this point in your education, you could do 4.41 plus or minus 1, you could do the math, right? So it's not important for me to know that the answer is, 3.7 to 5.9. It's more important to know this, right? One second, I'm looking for my other document here. Here we are. Okay. So going back to this problem. This is the problem we just did a few minutes ago about the paint cans, right? On an exam, yes, this is the correct answer, but it's okay to leave this as your answer. Okay? It's easier to grade when you use this than it is to do this. Because again,
There are so many different ways you can use rounding. That's why we want to know this. Okay? So tomorrow when we do this homework assignment, you're gonna answer your questions like this. Questions?
Can you go real quick how to find 1.86 on the last example?
How to get what?
1.86. Like,
Yep.
why-
Yep, I can show it there again. Okay. All right. At the top of the Z table, right? This top line here is confidence levels. 0.8, 8.09, 95, 98, 99, and 99.9. You're never gonna use this column. Okay? And again, these are for values all the way down to degrees of freedom of 35, and then it repeats over here starting with 36 and going down to 70. So we know we want 90% confident. So we go down, right? And then we know our degrees of, again, our N was 9, so our degrees of freedom are 8. So that would therefore use this value 1.860.
Oh, okay.
You're welcome. Okay. All right. So there are 2 assignments for tonight. So you're going to do the homework on confidence intervals, and then there's a couple of homework problems that deal with this topic here on the T, right? Unknown standard deviations. Okay. So that's it. If anybody wants to stay, I'll answer questions. Again, if you would like to have meet with me later on today, send me an email. But again, I mean, you can't send me an email at 4 saying, can I meet now? I'm not going to be around. So if you want to meet with me, you got to send it to me probably within the next half hour or so I can basically get on my schedule. Right? So let me know if you have any questions. I want to work with you. So again, at any point, send me an email. If I can't answer it, maybe Lucas can answer it. So between the 2 of us, we should be able to help you in the next few days. Okay? All right. So long, everybody. Thank you. And we'll see you tomorrow.